Okay, so we're going to solve a problem. We have a marble and it's rolling along a table here. And when it gets to the edge of the table, it leaves the table and it becomes a projectile. So it's going to follow a path that looks something like that. And we want to find out how far it goes horizontally. So the horizontal distance is the distance it goes from the point where it becomes airborne until the point it hits the ground. And we're trying to find that. So to solve this problem, we're going to treat it as two independent problems. So the ball is falling, that's one problem, that's a y problem, and the ball is moving horizontally, that's an x problem. So to do that, we're going to need to set up a variable list. So let's set up our variable list here. Okay, so there I have my variable list. In the y direction, I have the distance it travels, the initial velocity, the final velocity, the acceleration in the y direction, and the time. We know the acceleration in the y direction is always going to be negative 9.81 meters per second squared because it's due to gravity. And the other thing we know is that in the x direction, there's no acceleration at all. So that's going to be 0 meters per second squared. So as we read this problem, the ball is rolling along with a horizontal speed of 1.3 meters per second. So that tells us how fast it's going horizontally at the beginning of the problem. So that is going to be what we call the velocity in the x direction initial. That's going to be 1.3 meters per second. Now, if there's no acceleration, then the velocity in the x direction will never change, and so we can actually find the final velocity in the x direction, although it's not going to help us a whole lot. We are trying to find how long is the marble in the air, that's the time, and we're trying to figure out how far it goes horizontally, so we're trying to find delta x. Now, before we can really solve this problem, we need a coordinate system. We need a way to show where our axis is. So I'm going to draw a coordinate system. I'm going to call the point on the ground where the ball becomes a projectile, I'm going to call that my origin. So you can make a coordinate system anywhere you want, but it works best to make that the origin, right down here below the point where it becomes airborne. So now, what is delta y? How far does the ball travel vertically? Well, it starts on the table, which is 0.763 meters high, and it ends up at the ground. So delta y is always y final minus y initial, which is 0 minus 0.763. So the thing here, this is negative 0.763 meters. And it's negative because the ball travels downwards. Up is the positive direction, and so downwards means it's negative. We know one more thing here. The velocity initial in the y direction. Remember, the y direction is up and down. At the beginning of the problem, when the ball leaves the table, it is not moving up and down. So if it has a horizontal speed or it's horizontally launched, we know the initial velocity in the y direction is 0 meters per second. At the beginning of the problem, it's not moving in the y direction. Okay? All right, so now we're going to solve one of these two problems for the time. We do not know delta x, so we cannot solve the x problem. So we're going to have to solve the y problem. So the first part of our plan is going to be to solve the y problem, which is delta y equals the velocity in the y direction initial times time plus 1/2 the acceleration in the y direction times the time squared. We're going to try to solve this for the time. And so probably the easiest way to solve this is to realize that the velocity in the y direction initial is 0. So this thing right here is 0. So anything multiplied by it is also 0. So that's going to drop out. So we are going to have delta y equals 1/2 ayt squared. I'm going to write that one more time. That it's going to be delta y equals minus 1/2 of g t squared because the acceleration of the y is minus g. Now I'm going to try to solve this for t, so I'm going to multiply both sides by 2. So I'll get 2 delta y. Actually, let's do negative 2 delta y. That cancels that. So that equals gt squared. So if we divide both sides by g and take the square root, we can get that the time equals minus 2 delta y divided by g square root. And you might think you're going to have a problem here with the negative under the radical, but remember delta y is also negative, so those are going to cancel. All right, so at this point, you can just plug in the numbers, and I'm going to assume you can do that. So plugging in the numbers gets us a value of about 0.39 seconds. And remember, store this in your calculator. We don't want to use that rounded number. That's just a rounded number. Okay? So basically, by solving the y problem, we know that if a ball is launched horizontally, or if it's just dropped from the table, which is 0.763 meters high, it's going to take 0.39 seconds to hit the ground. So now we know the time. It's 0.39 seconds. And that's the same because the problem ends when we hit the ground. So it hits the ground on the y problem when it hits the ground on the x problem. So we're able to figure those two values out. Okay, now the second step we're going to do is we are going to solve the x problem. See, here we solved the y problem for the time. So now we're going to solve the x problem. So delta x, the distance that goes horizontally, is equal to the velocity in the x direction initial times the time, plus 1/2 the acceleration in the x times the time squared. And we're going to try to find the distance that goes horizontally. And this problem is easy because there is no acceleration in the x direction. So this is 0. So the distance it goes horizontally simply equals its initial velocity horizontally times the time. The initial velocity horizontally, we know right here is 1.3 meters per second. So it's going 1.3 meters per second, and it does that for a total of 0.39 seconds. Of course, I've kept this number in my calculator, so when I multiply it by 3, I get an accurate answer. And so I can plug that into my calculator and get a value of 0.513. 0.513, and that is going to be meters per second times second gives us meters. So the horizontal distance that the ball travels after leaving the table is 0.513 meters. Okay, so that's how we solve a projectile problem.